All right, next up, we have TJ Connolly, who's an engineer at Fireblocks. TJ is an engineer and consultant with over 10 years experience in the field of cybersecurity and software. He's going to be talking about DevSecOps for smart contracts. Without further ado, let's bring on TJ. Hey, TJ.
Perfect. Sounds great. Thanks. So for this talk today, I'm going to be talking about DevSecOps specifically for smart contracts. If you're not familiar with what smart contracts are, don't worry. By the end of this talk, you will, and you'll start to understand and take into consideration some of the unique security concerns that you have to be aware of when developing smart contracts versus traditional, software. And so what are we going to cover today? First off, we're just going to help define what is a smart contract. What is the typical DevOps lifecycle of a smart contract? Once we've identified what is the DevOps lifecycle, then we're able to construct a secure implementation of that DevOps lifecycle or DevSecOps. There's a lot of lessons, again, that we can learn from traditional DevSecOps and a lot of traditional tooling and processes that we can leverage. But there are some very unique things that you need to take in consideration when doing these on smart contracts and blockchains. And then lastly, I'll present a high-level framework on, if you are looking to implement a smart contract development program, how you can do so securely and some of the best and most widely used tools out there to do that. So first off, let's define what is a smart contract. Smart contract is a self-executing digital agreement. Effectively, it enables two parties to exchange anything in a transparent and conflict-free way while avoiding the need for a specific trusted party. So take, for example, you deposit money into your bank, right? You're trusting that your bank actually has that money, right? And when you go and you read your bank balance there on their website, you're trusting that, your physical cash is actually backed up there, or it's at least redeemable in some form or fashion. Smart contracts effectively eliminate the need for that trust in a counterparty. The trust, however, gets transitioned from the bank or this centralized entity to a decentralized blockchain. So that blockchain could be Ethereum, it could be Bitcoin, it could be there's a number of smart contract platforms out there, but effectively that's really what the trust assumption is that you're making there. You're taking the trust away from the centralized entity and put it into the decentralized blockchain. And so what is a smart contract? It's effectively just a software program that, is, Turing complete. It has collection of code, which are functions and data. So the state of that application, and they sit on that distributed ledger that is a blockchain. So you can contrast this to, the traditional client server or SaaS model where, code and data is, typically executed behind the scenes on a server somewhere, and you as the end user, you just see the browser or the mobile experience. With smart contracts, all of the business logic, so all of the things that typically might have been done on the back end are now done in a publicly verifiable and transparent manner. So if you interact with that smart contract, everyone can see what that smart contract does and verify that it executes according to what we trust it does. So there's a lot of positive attributes for smart contracts. Number one, they're permissionless by default. So that means that, anyone can go and deploy a smart contract on some of these open blockchain networks. They're also composable. So this is, huge in terms of interoperability. You can have a smart contract that calls another smart contract that calls another smart contract. And it really opens up the use cases for interoperability between, different applications. So instead of application needing to have its own proprietary API and other tools to have to integrate with that proprietary API, smart contracts all speak the same language. They all speak the same API. There's just unique kind of business logic things within the smart contract itself that you need to interact with. And then the big one is really just it's much more trustworthy. So the interactions with that smart contract, they're transparent, they're traceable, meaning that there's a ledger of truth. And it's, without breaking the security of the network, it's really traceable, right? So it's an audit trail that's built in, and who has interacted with that smart contract when and what did they do? And these are all very, very, positive attributes for certain use cases. That being said, with anything, there's always a trade-off. So, this could be considered a positive, trade-off or a negative one, but they're immutable by default. What does that mean? When you deploy a smart contract to a blockchain, by default, it can't be upgraded or updated, right? It's basically just you submit it, you send it to a block on the blockchain. It's now forever written to that block in the distributed ledger. And if you wanted to ever update that smart contract code, by default, you're not able to do that. There's workarounds for that, which we'll cover, but just, important thing to keep in mind here. The other, kind of risk here is that once you start talking about applications like DeFi, decentralized finance, and transferring a value and economic value, there is the potential for much more higher impact economic type security vulnerabilities. So in traditional software, when you're ingesting data, the worst case scenarios typically are I don't want to have remote code execution, or I don't want to let a hacker bypass authentication and authorization. Those concerns are still present with smart contracts, and even accelerated, so I would say. But on top of those, you also have this added cost of, hey, this is a public smart contract. Anyone can interact with it. If there are vulnerabilities in it, business logic vulnerabilities, then they could be much more higher impact, right? So if it's a lending smart contract that lends out, crypto when you post collateral, if that gets hacked, that entire lending market could be at risk. So these are very unique security concerns specific to smart contracts. And then the last two ones I just want to highlight there, performance at the blockchain is still a slower database. It's a slower centralized database, so it's not going to be valuable for every single use case out there. And again, the trust here that you're assuming is that the blockchain that this smart contract is settling on and living on is secure and decentralized and can be looked to as a source of truth. So how do smart contracts work? So a contract is deployed and managed by a human, a developer. You type your code, and then you deploy it to the blockchain. Once that smart contract is deployed on the blockchain, it exists there at a specific address. And then anyone else on that blockchain, as long as they're permissioned to do so, can then go ahead and view that smart contract and also interact with it. So what can they do with interaction? They can transfer funds directly to it. The smart contract can send funds out from the smart contract back to the users. And also the users can go and invoke specific functions or methods within that smart contract. So for the lending example, the high level contract it's a lending smart contract. One of the methods and functions there might be deposit, right? So you go and you deposit your collateral. Another one might be take out a loan. And so you go and invoke that. So they're all, delineated just like regular software would be with methods and functions. And so the important thing to understand here with blockchain, why this is so unique versus regular software, is that the ability for you as the developer to deploy that smart contract and then from there manage or interact with it as an end user, that is 100% dependent on the underlying authentication and authorization mechanisms of the blockchain itself. And so this is all done through public key cryptography and digital signatures. So this is what makes blockchains secure, makes them available to be decentralized, and enforces security without sacrificing some of those concerns. And so what you're going to find is that access control when it comes to smart contracts, it's really the biggest issue. It's critical to get that right and understand what are the threat vectors and how to design effective mitigations. So let's walk through what a typical smart contracts pipeline looks like. So, pretty similar to traditional software, you have your source code that you develop, mycontract.sol. I'm going to refer to a lot of things in this presentation in the Ethereum EVM kind of world. Ethereum is not the only blockchain out there that supports smart contracts. There's many others. But EVM is definitely the most widely adopted and has probably the most advanced developer tooling. So I think it's just a good frame to view this through. So you develop your source code, you then send it to the compiler. The compiler takes your source code, it generates the binary code from that. So you see that there, 0x21. And then you go and you actually have to deploy that code that you've now compiled to the blockchain. And you have to do that by writing it directly to the blockchain. So in order to write to the blockchain, you need an account on that blockchain. You need to actually write it, present that digital signature, and deploy it. What you should also do, and this isn't always required, but one of the big benefits of doing this on a public distributed ledger is that you can verify that the source code that gets deployed to the blockchain actually meets the source code that was compiled, right? So what this means is that if there was an attacker, a man in the middle that somehow, some way, was able to modify your code in between it being compiled and it being deployed to the blockchain, that the source code verification step would catch that and invalidate it, right? So, typical thing that you would do is you would, compile your code, deploy it, and then, verify that the code that was deployed at this address actually matches what you compiled. And then if it did, you're good to go. So once your application is deployed to the blockchain, it could be a mutable smart contract that doesn't change over time. There's no functions that really need to be updated, or it could be very kind of dynamic, and you need to be able to have the ability to do ongoing administration or other type of operations within that smart contract. So a typical one that you'll see is adding users or other addresses on the blockchain to an allow list or a deny list. So how are you able to do that? It's all determined by the underlying access control mechanisms of the blockchain. So this is very, very important. And what makes it even a little bit more confusing and challenging is that you have different layers of access control. You have who can talk to the smart contract and who has ownership of the smart contract and can do things from a high level with the smart contract. And then within the smart contract logic itself, the business logic, then you can also have additional access control layers depending on what you're trying to do. And then lastly, just want to talk about upgrades. Can you guys see my screen still? I think I might have.
Oh, we just lost it there, TJ.
Yeah, sorry about that. I think I clicked the wrong button. There we go. So upgrades, by default, like I said, smart contracts are immutable, but you do have the ability to, through different design patterns, specifically proxies, where you deploy a front end proxy contract that effectively points to another contract where your business logic is actually going to occur in. And the idea is that most of your updates and upgrades are going to be in the business logic side of things. So what you do is you just, with that proxy contract, you can point to a new business logic smart contract whenever you need to, deploy a new version. So let's talk about, the underlying authentication and authorization that's happening here. So, how is access control enforced by the blockchain and its public key cryptography? So, quick review of what that is. This is the combination of a public key and a private key that only Bob should know. At generation time, he generates this, typically within his crypto wallet. He provides a random seed. This might be a 12 to 24 word passphrase or, some random bytes. But ultimately with that, he gets, 2 pieces of cryptographic information, his public and private key deployed from that. And so what he does to transact on the blockchain is he'll go and, let's say he's trying to deploy, his code. What his wallet will do for him is it will produce a digital signature using both the public key, the private key, as well as the contents of the transaction. And what that does is that authorizes that transaction on the blockchain. So now the blockchain can say and knows that, yes, Bob has created the correct digital signature for this transaction. He provided, the correct public key that was also associated with it. And we can then go and verify that Bob is actually who he says he is because he has his private key. And we can go and execute this for him. So now Bob owns this contract that is now deployed on the blockchain. Now, let's say, for example, Bob wanted to transfer ownership of this smart contract to Alice. So Bob, within his wallet, again, he's going to execute another transaction. This transaction, though, is going to call a transfer ownership function. And he's going to transfer ownership of his contract, and he's going to send it to Alice, another user on the blockchain. And so again, His wallet's going to have to create a unique digital signature for this transaction that gets submitted. And then now the new world state of the blockchain is that instead of Bob owning the contract, now Alice owns it. And that's, the status quo moving forward. So what you're going to see here is really wallet security is absolutely critical. If you are storing your private keys in an insecure manner or using them operationally in an insecure manner, the entire security model kind of goes out the window. So it's extremely critical to get that right. So the other factor around that who is able to actually use those private keys. So thinking about developers, you're probably going to be using shared accounts here. So it's super important to have access control on who's able to do what. So within your wallet, you should have the ability to say, all right, this developer is able to deploy or update our smart contracts in different scenarios, and in other scenarios, what do we do? Do we block it and say, hey, that the developer, you shouldn't be doing that. That's anomalous. That could be a security risk. Do you have to go through multiple set of approvals or signatures for that? So this is where the concept of things like multi-sig come in. So instead of just saying one person, Bob, goes and approves this transaction, Bob now has to get his transaction also approved and also signed by M of N other individuals that he works with, really to provide checks and balances and also eliminate the single point of compromise of Bob's single private key. So this is going to protect really for anytime developer credentials are compromised, or there's a nefarious insider, one of the developers tries to push a malicious upgrade to steal funds. What if one of the developers, worst case scenario, is held at gunpoint? And really what your wallet infrastructure should have, and your wallet capabilities here should have, is the ability to have rules and controls that align to your business and effectively the known good baseline of what your typical DevOps operations look like. So your wallet should enforce that, such that if there's something that's anomalous, let's say Alice tries to go and provide an update or adds call a permission function within that smart contract, you should have logic and rules around that say, okay, this is anomalous. We're either going to go ahead and outright block that, or we're going to say that maybe in some possible scenario, Alice is doing this. We just need additional eyes on this and manual review, and make sure that you go ahead and do that. And so all of this needs to be managed by your wallet, because this is inherently where the security guarantees come from. It all comes from the private keys and the digital signatures that handle the authentication authorization on the blockchain. So I'm going to leave you here with a sample CI/CD pipeline, end-to-end for smart contract delivery. You're going to see, similar concepts here to traditional software. So, in the code section here, you obviously have your IDEs, version control. In the build stage, you have your compilers. In your test phase, one of the best and most important preventions of security vulnerabilities in software is just good, hygiene, right? Unit testing, making sure that your application performs as expected and as intended. Some other, unique considerations, obviously static and dynamic analysis definitely apply here as well. On the dynamic analysis front, this is, fuzzing, formal verification. So companies like Certora there, formal verification, although it can be used in traditional software, it's because of the economic impact of security vulnerabilities in smart contracts, formal verification is much more important, much more critical to use when you're talking about, the economic impact in smart contracts. Other tools that you're going to see here too, third-party audits. So, going out, getting a pen test or multiple pen tests and, publicly releasing those. And then also creating a bug bounty program, right? This is very natural to how this software gets deployed anyways. It's getting deployed in an open public system. Anyone can go and look at it. So you know for sure that the hackers are going to be looking at it as well. So you may as well provide them good incentives to come and report the vulnerabilities and get a reward versus going the black hat route. For the deployment here, Go
I'm
ahead.
super sorry to interrupt, man. In an effort to try and stick closer to schedule, if there's a way people can get in touch with you to ask questions further on, it's definitely super interesting. I do want to hear more, but I apologize based on the schedule to kind of cut you off a little bit here.
Yeah, no worries. Yeah,
How can people get in touch with you?
You can reach me on LinkedIn and on Twitter.
At TJ Connolly? Okay, cool.
Yep.
Well, thank you so much for presenting on this. Like I said, it's an interesting space and interesting to see how security plays a role in it as well, and what implications that's there. And I think you did a great job of at least introducing and bringing some insight into that for me. So thank you so much, TJ.
Awesome. Thanks, guys.
Thanks a lot, TJ.